Typically, novel physics is discovered when someone observes a discrepancy. This is evident in relation to Isaac Newton's physics. Hello everyone, welcome back to ZE, and today we brought to you another intriguing concept, the missing baryon problem and the antimatter discrepancy. Subscribe to our channel and let us find what mystery lies here. His physics remained, for a number of years, a perfectly accurate description of the universe that could be used to predict the behavior of moving objects. As time progressed, however, discrepancies were discovered, and as they mounted, new theories in the form of relativity and quantum theory were introduced to provide a clearer picture of how the universe operates, though Newtonian mechanics is still widely used. Albert Einstein and the expansion of the universe is another illustration. As did the majority of scientists at the time, he despised the notion that the universe was not inert and eternal, but rather had a beginning. As theoretical and observational evidence accumulated, however, it became clear that we exist in an expanding universe initiated by the Big Bang, and the scientific consensus shifted accordingly. The result was a more accurate, less contradictory description of the universe that is widely accepted today. Yet even with these new theories, discrepancies continue to arise, such as in the subatomic world, where relativity fails and quantum theory takes over, or in the interior of a black hole, where the known laws of physics cease to predict. The absent baryon problem is an example of a discrepancy that has yet to be completely resolved. Baryonic matter is what we observe and are composed of, with the term encompassing protons, neutrons, and all matter composed of them. There is a discrepancy between the amount of baryonic matter observed immediately after the Big Bang and what has been observed in more recent times. Studies of the cosmic microwave background radiation and studies of Big Bang nucleosynthesis have revealed that there are limits to the quantity of baryonic matter that resulted from the Big Bang. Great Bang nucleosynthesis is the process by which nuclei other than hydrogen formed in the very early universe, from the first few seconds to almost a half hour after the Great Bang. This is where the universe obtained its initial helium, as well as trace quantities of deuterium and lithium. It is also believed that radioactive tritium and beryllium-7 were created and then decayed into helium and lithium isotopes. The subsequent creation of all other elements in the universe occurred in the nuclear furnaces of stars. Given these circumstances, Big Bang nucleosynthesis ought to have produced predictable ratios of helium and lithium to hydrogen. This implies that approximately 4 to 5% of the energy content of the universe should be baryonic matter. This is consistent with evidence from the CMB, in which baryonic matter from the early universe has left an imprint. The numbers in this case are consistent, totaling approximately 5%. There are therefore two firm pieces of evidence establishing the amount of baryonic matter in the early universe. But it does not appear that this is the case today. In the interim, a large quantity of baryonic matter has mysteriously vanished. This ought not to be. The missing baryon problem should not be confounded with dark matter, which, as far as we know, is non-baryonic in nature. More on this shortly. This is getting close to the point where half of the universe's original matter is absent. It is difficult to determine the density of baryonic matter in the universe at present. Remember, it's all normal matter, so that can range from highly visible things like stars and galaxies to hard-to-see things like rocky planets and the dust and gas clouds of the universe, to rogue brown dwarfs and objects plying the intergalactic medium, and so on, to, of course, black holes, the number of which is highly debatable, especially if primordial black holes formed in the early universe do or do not exist. However, we can still derive a reasonable estimate based on what we know. Several useful phenomena include gravitational microlensing, where you can examine how much of this phenomenon you see overall, and clouds of dust and gas, which can be measured in a variety of ways, such as if they are backlit, or emit radio as hydrogen clouds do, in addition to other techniques sufficient to notice a significant discrepancy, especially when examining relatively recent galaxy surveys. The universe is absent approximately 39% of its original baryons after accounting for all of these factors. Then where did they go? Various solutions have been suggested. In 2017, it was proposed that difficult-to-detect frigid matter exists in intergalactic space between galaxies, which could account for it or the majority of it. This is supported by additional evidence from 2021, but it is not conclusive and needs further confirmation. This would imply that in addition to the majority of the universe's matter being composed of invisible, non-interacting dark matter, a large portion of normal matter is also virtually invisible due to circumstance, forming tendrils in the intergalactic space. Indeed, we inhabit a dismal universe. Time will tell if this explains the missing baryons, but this discovery reveals another enigma and discrepancy about the universe's matter. Where is every bit of antimatter? This enigma is referred to as the baryon asymmetry problem. Baryonic matter is ordinary matter, whereas antibaryonic matter is antimatter. The Big Bang should have produced equal quantities of both matter and antimatter, and if it had, all matter would have been destroyed. But this is not what we observe, and neither the standard model of particle physics nor general relativity can explain why the universe appears to have produced only normal matter during the Big Bang, at least in large quantities. There are numerous hypotheses as to why this is the case. The first possibility is that the laws of physics behaved differently in the past, or that some unknown factor contributed to the asymmetry that we do not yet completely comprehend. However, alternative options exist. One theory suggests that the universe was only slightly off, and that enormous quantities of matter and antimatter were produced in the Big Bang, but slightly more baryonic matter. As a consequence, a massive extinction event would have occurred, leaving only a remnant of normal matter, which comprises the baryonic matter we observe in the universe. However, there is an additional option that is quite frightening. Perhaps the universe is composed of both matter and antimatter, with the two forms being widely separated and concentrated in distinct regions. Strangely, an antimatter galaxy that contains no normal matter would appear identical from a distance to a normal matter galaxy. As long as the matter and antimatter components of the universe remain separate and never interacted, they could exist independently, and will likely continue to do so as the universe expands eternally. But if two galaxies of different types were to somehow collide, the result would be the annihilation of both galaxies, leaving behind only a massive discharge of energy in a perfect reaction and whatever form of matter remained from the more massive galaxy. Nonetheless, if this were true, there should be interaction at the intergalactic boundary between the two regions. Consider it the matter and antimatter zones. Deep in intergalactic space, the borderland should produce gamma radiation as a consequence of the destruction of matter. There has never been a detection of such radiation, and the current consensus is that antimatter galaxies probably do not exist. Another possibility is that matter and antimatter decay at distinct rates, allowing for the asymmetry. However, the concept of a mirror anti-universe may be the most intriguing aspect of this. There are multiple interpretations of the concept of a two-sided universe, one with a conventional universe and the other as an anti-universe extending backwards from the Big Bang. As a reflection of how the normal universe operates, the anti-universe would have reversed time, expanding in size the further back in time it travels. This concept has an intriguing effect in that it would actually explain the minute temperature fluctuations in the cosmic microwave background, implying that the universe and anti-universe are not necessarily exact mirror images of one another. In addition, it could provide an explanation for dark matter, as such a universe would produce heavy neutrinos that could suit the bill and provide a source for extremely high-energy cosmic rays. In addition, it could provide, in a sense, a home for the predicted antimatter product of the Big Bang. The antimatter is merely in the anti-universe, traveling through time backwards. This is consistent with past suggestions that antimatter behaves in a manner similar to normal matter moving backwards in time, although this is an oversimplification. Imagining such a dualistic antimatter-anti-universe is an interesting mental exercise, as it may resemble our own universe so closely that anti-humans on the other side could create small amounts of normal matter in their labs and marvel at how it disintegrates upon contact with antimatter. And naturally, the greatest mystery facing astrophysics is dark matter itself, where the gravitational effects of a vast quantity of matter in the universe are observed, but the matter itself is not visible. No explanation or detection of dark matter has been forthcoming as of yet. As a result, there are essentially three potential forms of matter that should be here or were here but may no longer be, but that we don't observe, which constitutes the vast majority of all matter in the universe, both normal and otherwise. Or if you prefer, the vast majority of the universe is AWOL, and it is possible that we will never know what or where everything went. Thank you for your time, everyone. How did you find the content? Is there anything you'd like to add? Tell us in the comments. Hearing from you is really helpful, and please subscribe to our channel for regular, in-depth explorations of the fascinating, strange, and unknown facets of our incredible universe.